Welcome everybody for this second day of the conference. Hope you are all rested. Today there are a lot of very interesting talk. So we will start with Viviane Baladi. And in some sense, she is from Paris at the Laboratoire de Probabilité Statistique and Modélisation and also Sorbonne. But actually, she is in some sense a local, since she got her PhD in Geneva with Jean-Pierre Ekman. And since then, she has moved a lot. Too far away. OK. Can you hear me now? So since then, she has moved a lot. She has been in many universities in Paris, but also she spent quite some time in Zurich, in Geneva, and she's been associated to HS. She spent time in Copenhagen, in Rio, and so on and so forth. So her work was starting with the study of Ruelle zeta function. That's actually the first time I heard about her. She was a young lady putting out a lot of very strong results on the subject and already establishing herself as a leader in the field. Then she has worked on unimodal map, random system, but most of all, statistical properties of dynamical system. So that is a field that is kind of very relevant, for example, for non-equilibrium statistical mechanics. And she has obtained several results in this field. And notably, in the last 15 years, she has been one of the main promoters of what is loosely called functional approach to statistical properties. It's some kind of refinement of an old idea due maybe to study the Koopman operators that trace back to the mean-ergodic theorem by von Neumann, and has seen quite a few exciting developments in the last years. She also had very interesting result on linear response, another field of clear relevance for non-equilibrium statistical mechanics. And lately, she has been focusing also on billiards, that also has relevance for physics. So her work has been variously recognized. I mean, she got the Médaille d'Argent from CNRS. She's a member of the European Academy. She's currently holding a ERC European grant, and she was an invited speaker at the ECM in Seoul in 2014. So the last thing I would like to say about her is not directly related to her research, but is an activity that I think is very important. She was really extremely energetic in doing service to the community. Apart from being editor in a lot of journals, I mean, she's currently editor of Invenciones, but she has been editor of Transaction, publication of the IHS, and many, many others. Also, she always has been extremely active in organizing and being part of committee, but most of all organizing conferences and stuff like that. And she's, I think, left a lasting influence on the community, especially for young researchers. So I think that with this, I will leave the word to Viviane, that is going to talk. Of course, as usual, I forget the title, Billiard. Well, whatever. You can read the title. I mean, I'm sorry, I'm very forgetful, it's age. But before giving her the word, I have to give her the medal. So this is just in occasion of this presentation of yours. So please, you have the floor. Thanks a lot.
OK, thank you very much for this very nice introduction. So yes, and reminding everybody that I was a young lady 30 years ago. Yes, thank you. You forgot, but I should. Yeah, I'm following your example.
Yes, but I will
No, I know. OK, good morning, everybody. So yes, in some sense, I'm a local. I graduated from the University of Geneva. But before that, more importantly, I learned that it was not cool to say 80 and you should say 80, because I was born in Canton de Vaud, actually. And I also learned integration by parts, which is maybe even more important for my career. So today I'm going to try to talk to you about Sinai Billiards. And yes, it works. So I have a plan. I'm not sure I will be able to go to the end, because I would like to get some information through, and so maybe I will go a little bit more slowly than I planned. First, I will remind you what are Sinai Billiards, and there are two versions, a discrete time version, which is a map, and the continuous time version, which is a flow. And then I remind you just of 2 or 3 of the important classical results, mostly by Yasha Sinai and Alai Sang-Yong, and also maybe I briefly mentioned some work of Chernoff. And classical results, let's say it was the 20th century. But what I would like to present today are the results from the past 10 years, which use this functional analysis approach that Carlangelo Viviane alluded to. And I will start this discussion by mentioning a paper which appeared exactly 10 years ago, and which gives a new proof of one of the classical results which I will have presented just before. And then there are 3 theorems that I would like to present about the billiard flow and about the billiard map. So for the moment, the titles look a little bit mysterious to many of you, but I hope that it will become clear. And then if I have time, I will mention some openings for future work. So what is a Sinai Billiard? So actually, I put Sinai Billiard in the title, maybe because it's more catchy, but what I will talk about is slightly more general. It's what is called a dispersive billiard. So what is a dispersive billiard table? So you take the 2 torus and you remove finitely many obstacles, which are called the scatterers. And what's important is that they are disjoint. So the closures are disjoint. And the other thing which is very important is that the boundaries have strictly positive curvature. And the boundaries need to be at least C3, okay? So on the pictures, there are perfect circles, perfect disks. I give you 2 examples of Sinai billiard tables. Sometimes in the literature, the expression Sinai billiard refers only to the billiard with a single disk in the torus, a single scatterer. But as I said, it's a little bit more general today. We can have boundaries which are not perfect circles, but they have to be strictly convex. Okay, and so that's the table, that's the billiard table. And now what is the dynamics? So as I said, there are 2 ways of viewing the dynamics, either in continuous time, so the billiard flow, which maybe is more the most natural mechanical model. So it's a single point particle, just one particle, which moves at unit speed along straight lines as long as it's on the table. And when it meets one of the obstacles, so the boundary of one of these obstacles, then there is a specular reflection, so the incoming and outgoing angles are the same. So that's the flow, so just continuous time. And then what is a billiard map? The billiard map is a map which goes from collision to collision. It's also called the collision map. So then the map acts on a space M, which is a product of the boundary of the table and the angle, which in the standard coordinates is between -π/2 and π/2. And these coordinates are obtained by looking at the arc length along the boundaries of the obstacles and the angle, which is traditionally measured after the collision and with respect to the normal to the boundary. So by the way, normally I only give Blackboard talks, so I made an exception for today. But as you can see from this picture, I'm completely incompetent with preparing my slides. And you can see that the varphi was not compiled correctly. OK, so I hope this model is clear to everybody. So it's embarrassingly simple to describe, but it's actually quite difficult to study mathematically. And the reason is because although the flow is continuous, it's not differentiable. The derivative blows up along the so-called grazing trajectories. So the grazing or tangential trajectories are those which barely hit an obstacle. So the angle is either plus or minus π/2 in the coordinates I just described. And these grazing trajectories or tangential collisions, they even cause discontinuities in the map. So the flow is continuous, but it's not differentiable. So there are singularities in the derivative. And the map is not even continuous. And I leave it as an exercise. If you never thought about billiards before, you can try to prove that the map T is piecewise 1/2 Hölder. And this 1/2 Hölder, well, just think about the case of the perfect circle. You get the square root, which come from the equations of the circle. OK, and so I will introduce some notation. It will not be used so many times. But just to introduce the singularity sets. So the initial singularity set is a set of these tangential collisions. So all points for which the angle is equal to plus or minus π/2. And as we're talking about dynamics, we have to iterate this set in the future and in the past. And so this initial set S0 looks quite harmless. It's just finitely many circles, right? Because we have finitely many obstacles. But when you iterate it, you get a countable set of curves. And this set of curves is dense. So you have singularities all over the place. And they really mess up very badly with analysis. So that was the bad news. Now there are some good news. And the good news is that the billiard is uniformly hyperbolic. So you have invariant cones for the derivative. So you have an unstable cone, which is mapped strictly into itself by the forward dynamics, and a stable cone, which is mapped strictly into itself by the derivative of the inverse dynamics. And these cones have very simple equations. So kappa, or big K, was a curvature. Remember that the curvature was C3. And so it's bounded from above. And by convexity, it's bounded from below. So you have this K min and K max. And the free flight time is denoted by tau. And remember that the obstacles are strictly disjoint. So there is a lower bound for this time, and which appears in these definitions. And you can also, this is also an exercise. You can check that these cones are strictly invariant. And what you should think of are, focusing or dispersing fronts of trajectories. OK, so that's good news because we have a lot of tools to understand uniformly hyperbolic dynamical systems. But because of the singularities, we will have problems. So not only we have these invariant cones, but actually we have a quantification. We have a number strictly bigger than 1, which says how fast we expand in the future, and 1 over lambda says how fast we contract. And this is, of course, the expansion takes place in the expanding cone, and the contraction takes place in the contracting cone. Okay, so this is what allows us to tackle this problem. Okay, so now the classical results. So for the flow is Hamiltonian. So Lebesgue measure is preserved. So that's a good starting point. And the map, it doesn't preserve a Lebesgue measure, but it preserves an absolutely continuous probability measure, which has this very simple formula. It's just a cosine. The density is just up to normalization, the cosine of this angle phi. And so we have a very nice invariant, absolutely continuous invariant measure for both the map and the flow. So of course, what you want to know if this measure is ergodic. Because once it's ergodic, then you know that the time average consists with space averages, and that's what we like, right? Both as mathematicians and as physicists. And this was the first very deep result on billiards, which was obtained by Sinai more than 50 years ago now. So he proved that for the map, this measure, which is called also SRB measure, which means Sinai Ruelle Bowen. So this invariant measure for the map is a unique absolutely continuous invariant measure. Lebesgue measure is a unique absolutely continuous invariant measure for the billiard flow. Okay, good. And in addition, not only are they ergodic, but they are actually mixing, so strongly mixing. And actually, I think he also proved a K property. So mixing, there will be some formulas very soon, but I guess most of you know what it means, and it's a form of independence, which is, as I said, stronger than ergodicity. And a few years after that, Galabotti and Ornstein proved a slightly stronger mixing property, which is a Bernoulli property. So we know that we have this asymptotic independence, but at the time, we didn't know how fast it took place. And this is a second very important result, which I skip a lot of things, right? I mean, there are a lot of things that we know about billiards, but I have to skip. So the second classical result I want to mention is about the speed of mixing. And this is a result by Lai Sang-Yang in 98. So Lai Sang-Yang did it in the case of Finite Horizon. Chernoff did it soon thereafter for Infinite Horizon. I will get Finite Horizon in a moment. And what they got is exponential speed of mixing. So the meaning of exponential mixing is given by this formula in the last line. This mouse is not very stable. No. Okay. So it's given by this formula in the last line, and it means that when you have two observables, which need to be at least Hölder, when you integrate the product of one observable and the other iterated by the dynamics, this converges to the product of the average of the observables at a speed which is exponential with a rate which only depends on the regularity of the observables, although there is a prefactor, which is noted C psi 1, psi 2 here, which could depend on the observables. So it took almost 25 years between the mixing and the speed of mixing. And I should insist on the fact that this result of Lai Sang-Yang was only for the map, so only for discrete time, the discrete time billiard. And these results were proved by using symbolic dynamics, and I will explain in a moment why, if you want to get the result for the flow, it's better to use a different approach. And this is a definition which I promised. Finite horizon. So finite horizon means that there are no trajectories which make only tangential collisions. And you have to think about it for a while, but actually this is a slightly stronger condition than implying that there are no trajectories which have only one collision. So in other words, this condition implies that the maximal free time is bounded, and actually it's uniformly bounded. So what about the speed of mixing? So there were some results with this finite horizon condition, which were proved by using also this symbolic dynamics method, but they were not optimal. So there was a result by Melbourne, which got faster than any polynomial for the billiard flow, and a result by Chernoff, who proved stretch exponential speed for the billiard flow. So stretch exponential means that you have this, instead of exponential of minus a time, you have exponential of minus square of the time. And I just want to, this is the only thing I'm going to say about Infinite Horizon. It's just to point out that it's really different. It's not just that we are stupid and we cannot get better results in Infinite Horizon. Infinite Horizon, the speed of mixing is very slow. It's just 1 over the time. OK, now let's move to the new results. And as I mentioned briefly already, the tool that Lai Sang-Young used is an extremely powerful tool that actually she mainly developed, which is basically an infinite countable Markov partition for the billiard. So there were some previous work by Bunimovic, Chernoff, Sinai, etc. But she kind of perfected this approach by constructing what is called now a Lai Sang-Young tower, which has been used in many other settings. However, when you reduce to a symbolic setting, you lose a lot of information. But 10 years ago, Mark Demers and Hong Kong Zhang gave a new proof of this theorem, which was in the previous slide, the theorem of exponential mixing for the billiard map. Right? Now we're back to maps. And what they used is a Ruelle transfer operator. So the Ruelle transfer operator was also appearing in the approach by Lai Sang-Young, but for the symbolic dynamics. Here we have the Ruelle transfer operator, which is just defined on the manifold. Okay? No symbolic construction. You just compose with a dynamics, with a backwards dynamics. So the formula is on the slide. And you see from this definition that you divide by the Jacobian. And this implies that the dual of the operator preserves the Lebesgue measure. So why? Because we want to construct with this operator, to construct and study a measure which is absolutely continuous with respect to Lebesgue. So it's natural to have an operator which, the dual of which preserves the Lebesgue measure. OK, and now the trick is that you have to have this operator, to let this operator act on the right space. If you let it act on continuous function, you get a whole disk. The closed unit disk is going to be the spectrum, and that's not interesting at all. Or L2 of Lebesgue, it doesn't help, right? So what you have to do is you have to use a space which exploits the smoothness of the dynamics. But since you have contraction and expansion for the same dynamical system, when you compose with the contraction, it improves smoothness. So then you want to have smooth, a norm which likes smoothness in the unstable direction, but you want a norm which likes the dual of smoothness in the stable direction. And these are these anisotropic Banach spaces. So they had been introduced previously in a paper by Blank, Keller, and Livarani. There's a lot of literature. I think it will appear in tiny at the end of this slide. But let's just skip to the paper which is relevant for billiards, which was a paper by Demers and Livarani, which adapted this initial construction, which worked only for the Anosov or Axiom A maps, to handle piecewise smooth maps. And so it was upgraded from piecewise smooth to billiards by Demers Zhang in 2011. And this is just like a disclaimer to say that there are many people I should cite, and I don't have the time, so let's just skip. So what did they do? So they had to adapt this norm by introducing some tool to take into account the fact that the billiard map is not differentiable. So if you want to control a distortion, you need to work with something called homogeneity layers, which are just it's a countable partition of the phase space, which becomes much more thin when you get close to the singularities. And there's another enemy that you have to fight, which is the fact that when you iterate the partition, the elements of the partitions where you have smoothness could have a big multiplicity close to any given point. So this means that the complexity of the system can grow. And you have to make sure that the hyperbolicity wins against the complexity. And this is done by something which is called a growth lemmas. And so both the homogeneity layers and the growth lemmas were constructed, were introduced before by Chernoff and other people. But Demers and Zhang were able to introduce these tools into this functional approach. And so what you do once you have these tools, you have to study the spectrum of this operator on this Banach space. I think I have a picture, yes. So the first thing you want to, the operator is not compact. It's not a compact operator. But it's quasi-compact. It's almost compact, meaning that the essential spectrum is inside some disk, which is strictly smaller than the unit disk. So the spectral radius of this operator is equal to 1. Remember that we have a fixed point for the duo, which is Lebesgue measure, so you're not surprised that there will be a fixed point for the operator itself. Actually, 1 is equal to the spectral radius. But all the essential spectrum is contained in a disk which is strictly smaller. So that's the first thing that you have to do. And the technical tool is what is called a Lazotta-York or Dublin Fortet estimate, which means that you show, by using the norm that you devised, that the operator is a contraction modulo some compact error term. OK, that's the first thing. And the second thing, you have to study the eigenvalues which are outside of this small disk. And the most interesting one is the eigenvalue 1, because that will correspond to this absolutely continuous invariant measure. And so they show that this eigenvalue 1 is simple, and that there are no other peripheral eigenvalues, no other eigenvalues on the unit circle. And this is similar to the properties of positive matrices, finite dimensional matrices, so the Perron-Frobenius theorem. And it implies that you have a spectral gap. And of course, once you have the spectral gap, you can imagine that you get exponential mixing from that. And the eigenvalues inside this open annulus, so between theta, so the value of the essential spectral radius, and 1, are the Ruelle resonances. OK, so I already mentioned that you get the exponential decay from the spectral gap. And if you want, you can use these other resonances to get a more precise asymptotic expansion for the correlation function. And in that paper, they show many other things. In particular, by using some spectral perturbation theory, you can show that the rate of mixing is stable if you change a little bit the billiard table. And what is important for that is that you work with these cones, which are stable when you change a little bit the billiard. And something which is quite important, actually, but it was only proved 10 years later. So we have this eigenvalue 1, which is really there. It corresponds to this absolutely continuous invariant measure. And then I mentioned if there are some eigenvalues in this annulus, they are called the Ruelle resonances. And you can use them to get this asymptotic expansion. But it's only last year that Damien Thomine constructed examples showing that there are some billiard tables for which non-trivial Ruelle resonances exist. Well, Ruelle resonances exist in the terminology which I mentioned. OK, so that was a breakthrough because, as I explained, it used the dynamics on the manifold and not this symbolic construction which was used by previous authors. And this was a key to show the exponential mixing of the flow, which is a result with Mark Demers and Carlangelo Liverani, which took almost 10 years to get. So it was very hard to obtain this result. And what we got is exactly the same result that Lai-Sang Yang proved for the map, but we got it for the flow. So flows are more difficult than maps because when you have a flow, you always have the direction of the flow along which there is, of course, neither expansion nor contraction because you just move along this direction. And this creates a lot of technical problems. But nevertheless, we got this result. And so it's a paper which I think has 140 pages, but I will summarize it in one slide. So the point is that we use a transfer operator acting on the manifold, or acting on a suitable Banach space of anisotropic distributions on the manifold. And this will be very important to get the spectral gap. So there are some variants when you study the flow. Instead of using the semi-group of operators, you study actually the generator of the flow. And the first step is actually not so hard, or is relatively easy, is to show that the spectrum of this generator in some half plane which contains the zero contains only countably many isolated eigenvalues of finite multiplicity. So what I should mention, this is probably clear to most of you, but the big difference between the map and the flow at the level of the operator is that for the map, you had the operator was a bounded operator, so the spectrum was in a disk. The generator is not bounded. It's closed, but it's not bounded. And so now you're talking about half planes, and so you can have lots of problems because instead of having an annulus, which is compact, you will have strips which are not compact. And so if you have this first property of the control of the spectral gap, the quasi-compactness, you're not done, because the eigenvalues could accumulate on the imaginary axis. And that's the second step in the proof, which is a really hard step, which used some estimates which were developed in the thesis of Dima Dolgopiat to exploit some oscillatory integrals to get better control on the resolvent of this generator and show that the enemy can be fighted against, meaning that these resonances do not accumulate on the imaginary axis. So there is a half plane on which the only element of the spectrum is 0. So by the way, 0 before was 1, because when you go from the semi-group to the generator, there's a logarithm or an exponential. But so 0 now is what was 1 before. OK, and now the punchline is that to exploit these Dolgopiat estimates, you need that there is an invariant contact form. So you use the fact that flow is Hamiltonian. And this was an important property of the dynamics, which was lost when you use the symbolic dynamics. So this is why this functional approach is much more powerful for this particular problem. And there's a technical issue about the Kalash was probably horrified. It's a very important element of the proof, but it's quite technical. And the fact is that there are stable and unstable foliations for hyperbolic dynamical systems. For Anosov flows, they are Hölder, which is already a little bit stressful for some geometers because they don't like foliations which are not differentiable. But for billiards, the foliations are not even Hölder. They're just measurable. So you have a foliation which is just, the cones are nice, but the foliations are just measurable. And so in the proof, in some steps of the proof, you really need to work with some foliation which is nice. And what you use, they use some approximate foliation. OK, this I just skipped. OK, so that was about the flows. So that was the first important result, which was obtained by using this functional approach for billiards. And now I want to mention a couple of other results. And now we're going back to the map. OK, now we have a rather complete understanding of the Liouville or Lebesgue measure for the flow. Now let's go back to the map. And the question that you can ask is, what about other invariant probability measures? So the absolutely continuous one is, in some sense, the most natural, because it describes the time averages of Lebesgue almost every initial condition. But there are other natural invariant measures. And the first one we wanted to study was the one which maximized the measure theoretical, the Kolmogorov entropy. So this is a natural question, and in particular for the situation of geodesic flows in negative curvature, this is the measure maximal entropy is the Margulis measure, and studying this measure gave a lot of information about geodesic flows. So as I said, our friend is hyperbolicity, our enemy is singularities. So the hyperbolicity implies that the map is expansive. The map is acting on a compact set because the billiard table is compact and the set of possible angles is compact. So you could think, okay, you have an expansive map on a compact set, so then the Kolmogorov entropy will be upper semi-continuous, so you will have to have a maximum, the maximum has to be realized and you're done. But if you make this reasoning, you are forgetting one important fact, which is that the map is not continuous. So you have an invertible map on a compact set, which has good hyperbolicity properties, but it's not continuous. It's continuous if you removed all the iterated singularities, but as I said, this is a dense union of a countable union of curves. So once you remove this set, you are left with something, but it's not compact. So you're also in trouble. So the naive approach does not work. So you have to, make some preparations. And the first preparation is we don't know yet if the maximum of the entropy is realized, but let's just guess. And in some sense, you could argue that we are using the functional approach to study these problems, but on the side, we still use some more topological or symbolic tools. So we kind of mix, you have to use all the tools that are available if you want to solve these problems. And so the first thing that you do is you make up a reasonable candidate for the maximum of the entropy. And what you do for this is that you take the singularity curves which have been constructed up to level n. So this cuts up your space into a finite number of maximal connected components. You count the number of components. You take the log, you divide by n, and then you take the limb sup. And this gives you a number, a positive number. And you call it h star, and that's your first step. OK, and then there's a second step, which actually, of course, did not appear until we had spent many months trying to solve this problem. We expected that it would be possible to show the existence of a measure of maximum entropy for all Sinai billiards. We could not do it. We needed an assumption. So what is the assumption that we need? We needed to assume that the orbits, of course, can have grazing trajectories. And actually, you cannot exclude two successive grazing trajectories. But you would like to avoid that there are too many grazing or almost grazing trajectories for the billiard orbits. So you have to quantify this. So you fix some number very close to pi over 2. You fix some very large integer n0. And then you say that you have sparse recurrence to singularities. If the number S0, which is such that all orbits of length n0 have at most S0, n0 collisions with value, absolute value of the angle bigger than phi 0, so that this number S0 is small enough, and meaning that the condition B, which is written here, is satisfied, meaning that the candidate for the topological entropy H star is strictly bigger than S0 times log 2. OK, so S0 is some kind of asymptotic proportion of recurrence to the singular set. And you want this number to be smaller than the topological, or than the candidate for the topological entropy up to this factor log 2. So this factor log 2 does not come out of the blue. It comes from the fact that when you hit, when you're very close to a singularity, you have some control on how much stable curve can be expanded. And this stable curve is, again, this square root which appeared previously. And I put a little comment here. The fact that S0 is strictly smaller than 1 is because we assume finite horizon. And if you have a billiard table which has double tangencies, this you cannot exclude, but no triple tangencies, then you can choose phi 0 close enough to pi over 2 and n 0 large enough such that this number S0 is not bigger than 2/3. What I'm trying to point out here is that this condition is a checkable condition. I mean, once you have for some billiard tables, it's possible to estimate the S0, and then it's possible to show that there are billiard tables which satisfy this sparse recurrence. And actually, the two examples which I saw on the previous slide do satisfy these sparse recurrence conditions for many choices of the parameters which appeared in the picture. And actually, we don't have any single example of a map which does not satisfy this condition. It would be quite interesting to have examples, and then maybe to try to investigate these examples more carefully. OK, now you guess the result. We assume this condition of sparse recurrence to singularities. Then we have a unique measure of maximum entropy, mu star. The Kolmogorov entropy of this measure is equal to H star. So this candidate H star for the topological entropy was correct. And then we have some information about this measure. So it doesn't have atoms. It's not absolutely continuous, right? So it could be a priori very strange, but it does not have atoms. It charges all open sets, so it has full support. It is mixing. Actually, it's even Bernoulli. And it has a property which is very important, actually, for billiards. I did not mention it, but Lebesgue measure or the SRB measure do have this property, which is written on the slide, of being adapted. So this measure of maximum entropy is adapted, so it does not give too much weight to the singular set. And actually, we have a more precise information, which I don't have the time to discuss, about the measure of the neighborhoods of the singular sets. OK, and there's a necessary condition for the measure of maximum entropy to be equal to the SRB measure, which is very strong, which says that the multipliers of all the periodic orbits are the same. We conjecture that this condition is never satisfied, so that the measure of maximum entropy is always different from the absolutely continuous variant measure. But we don't have a proof of this conjecture. And one last thing, a little bonus. There are actually a lot of work using the symbolic approach. In particular, there is a very nice paper by Lima and Mateus using the symbolic approach. And they get a lot of results for billiards. However, their starting point is this condition of being adapted. So their result only works if you already know that you have a measure which satisfies this property. And they could not prove it. So we constructed a measure. We proved that it satisfies this property. And then we can use some of their, so it's what I was saying before, you should use all the tools which are available. So once we have the measure, we can show that the number of fixed points is bounded from below by the exponential of the topological entropy to the correct power. OK, so this looks very nice, but there's something missing, which maybe some of you have noticed. So this I skip. I didn't. OK, I have to say it because I didn't dare to write it. There's something missing, which is the speed of mixing. We were not able to control the speed of mixing. And the proof will explain why. So again, we use this functional approach. So we have a transfer operator. But of course, it's not the same transfer operator. The previous transfer operator had a dual which preserved Lebesgue. Now we need a transfer operator with a different potential. And the one which is relevant for the measure of maximum entropy is a potential where you divide by the stable Jacobian. Now, the stable Jacobian is a little bit annoying because sometimes it goes to 0. So sometimes you're dividing by 0. Yes, I even wrote it. So sometimes you divide by 0, so that's a bit annoying. And how did we solve this problem? We completely abandoned the hope to control distortion. So we gave up the approach using homogeneity layers. And instead of using a Hölder modulus of continuity, we had a logarithmic modulus of continuity. So this allowed us to construct the measure, but we lost the spectral gap. So we have a transfer operator, we have control of the spectral radius, it's exponential of this candidate for the topological entropy. We have a maximal eigenvector for the operator, we have a maximal eigenvector for the dual. We put them together to construct the measure of maximum entropy, but we don't have a spectral gap, and that's why we could not get the exponential mixing. Okay, so that was for the measure of maximum entropy for the billiard map. And the last result I want to mention is another joint work with Mark Demers. And this is for still for the billiard map. We now want to look at other equilibrium states. So both the SRB measure and the measure of maximum entropy are Gibbs state or equilibrium states. And it's very natural to try to look at the one-parameter family of equilibrium states for the potential, which is minus t times the logarithm of the unstable Jacobian. So if you take t equal 1, you get the SRB measure. If you take t equals 0, you get the measure of maximum entropy. But we want to get the whole one-parameter family of equilibrium states. So how do we do this? First of all, we define the pressure. So what is the pressure for a number t bigger than 0? It's a supremum of the Kolmogorov entropy minus t times the average of the unstable Jacobian with respect to mu. And mu ranges over all t invariant Borel probability measures for the map, right? Now we're back studying the map. So by definition, if the supremum is attained, then the measure or the measures, if there are several, which realize the supremum are called equilibrium states. So that's just a definition. And our little remark, which actually I already hinted at, if you take t equals 1, then the pressure is equal to 0. And this corresponds to the pressure realized by the SRB measure. And in fact, it is known that if you have another invariant probability measure, which does not give too much weight to the boundaries of this neighborhood of singularity sets, then the pressure, the corresponding pressure will be non-negative. So we had some information for the value t equals 1. So what did we prove? So this is a more recent paper, which is only on the archive. We proved that there is a window, so between 0 and some number t star, which is strictly bigger than 1, so to the right of the value 1 for which we have this good understanding. So there's a window of parameters for which everything goes fine, meaning that we have a unique equilibrium state for minus t log of the unstable Jacobian. But not only that, we have a measure, which is, this measure is mixing, gives positive mass to open sets, does not have atoms, it's t-adapted. And we have the spectral gap, so we get the exponential decay of correlations for Hölder observables. And maybe you noticed that the parameters go from 0 to t star, but the value 0 is not part of the admissible parameters. But if we make the assumption that I stated before of sparse recurrence to singularities, then we know that the measure maximal entropy exists, and we can prove that the pressure, when t goes to 0, the pressure of t converges to this topological entropy that was discussed in the previous theorem. So by now, you probably guessed how the proof looks. So first of all, we introduce a candidate for the pressure, like a topological candidate, by using, again, this refined partition. And we prove some basic things about it. It's convex, it's strictly decreasing. And it behaves, it's an upper bound for the actual pressure. And the heart of the proof, again, is to prove a claim on the spectrum of a suitable transfer operator. And I didn't put it in red, but you can see that the weight here is the bad guy, so the stable Jacobian, but to the power 1 minus t. And since t is strictly positive, the power of this stable Jacobian is always strictly smaller than 1, and this is the reason why it's much easier to study this operator than the operator in the previous argument. So we use an anisotropic Banach space, which is the same one which was used by Demas-Jung. So again, we have the homogeneity layers and a nice control of distortion. And because of that, we can show that not only we have a good control of the maximal eigenvector, but we have a spectral gap, which gives this exponential mixing property that we all love. So I think actually that's the end of the result. So maybe let me just quickly, no, I had more information. But yeah, I think I will skip that. The essence of this slide is that you have a nice control, but when t goes to 0 or when t goes to t star, everything blows up, and in particular, the spectral gap goes to 0. So when we go to 0, we cannot control the rate of mixing, and which is consistent with the fact that we were not able to prove exponential mixing for the measure of maximal entropy of the billiard. Yeah, this I skip. Okay, and now there are a couple of byproducts. So we get analyticity of the pressure. We have a formula for the first derivative. We have a formula for the second derivative, which are the usual formulas that probably many of you have seen in different contexts, either in dynamics or in statistical mechanics. And we have strict convexity, meaning that we know that the second derivative of the pressure vanishes only if we have a solution to this co-boundary equation. Meaning that we have an L2 function such that the stable Jacobian up to the corresponding co-boundary is equal to a constant. And of course, we don't know any examples satisfying this property, and we conjecture that it doesn't exist. We conjecture that the second derivative is always strictly positive. Okay, this I skip. And we also have a central limit theorem, the usual central limit theorem for these equilibrium states. So I skip that because I just want to spend a few seconds. I want to keep some time for questions to mention that there are several open questions which remain. So as I said, the measure of maximal entropy, we only studied it for the map. And there is some ongoing work in the Paris group to construct an invariant measure for the flow. And actually, my student Jérôme told me yesterday that he had some good news, but I won't mention his last name because it's not sure yet, but we are optimistic again. Another project on which we are working in Paris is to try to understand if we can get any control on the speed of mixing for the measure maximal entropy for the billiard map. So these are projects that we are working on, but I don't want to state any results because it's too early. And there are many open problems. I told you that Tomin found examples of billiards where you can exhibit explicit Ruelle resonances. But for the flow, we don't have any example. We know that there is a gap. We know that after the gap, there are at most countably many Ruelle resonances, but we don't know any example where there is at least one resonance. At least I don't know, maybe Calangelo knows, but I don't. I told you about this sparse recurrence condition to singularities. I told you we don't know any example where it is not satisfied. We would like to show that, we would like to know whether it's generic, either in the measure theoretical or in the topological sense. That would be really interesting. We would like to know if the measure maximal entropy and the SRB measure of the map never coincide. And the last two questions are maybe more difficult. I told you there's a lower bound on the number of fixed points given by our construction of the measure maximal entropy. We would like to have the upper bound, and the upper bound is much more difficult. For the moment, we don't know how to get it. And even more conjectural would be to construct a dynamical zeta function. So it's back to my young days, right? To construct a dynamical zeta function whose poles are in bijection with Ruelle resonances. But this is really, we don't really know. Well, actually, we have some ideas, but they are very sketchy. So I will stop now. Thank you very much for your attention.
So there is some question from the audience in presence. Yes? Yeah, you have to push the button, I think, yeah? No?
Hello.
Wait.
Oh, okay.
Okay.
Yeah, I have a question concerning MME of maps.
Yes.
Can you show that slide?
I can try.
Can you go back?
Yes. Yes.
A little more?
More.
This condition number 2.
Ah, yes.
Yeah, preparation
Yes.
2. So
Yes.
I wonder whether there is any relation between this condition, which I don't understand, and you know what people did about maps of the interval, in the sense that assume that I take a family of billiards and I vary the radius. Is it then true that for a positive set of radii, this condition is true, or something like that? You understand the question?
Yeah. So I think I understand the question. So actually, I didn't mention it, but once I was giving a talk, and then Pierre-Antoine Guilleneuf conjectured that if you take a set of billiard tables and you put suitable parameters, then the condition would be satisfied for almost every parameters. And what you suggest is a concrete example of a very simple model. And maybe you're right. Maybe that would be the starting point, just to look at this shrinking.
Yeah, you know, this was painful, right? But somehow you have to measure how often you have this recurrence to a singularity as a function of the parameter, and then you eliminate parameter. I don't know whether this is doable or not. Okay.
But you cannot make the diameter shrink too much, right? Because then you have infinite horizons.
No, just you know what happens in maps is that near certain parameters you have Lebesgue density, right? So there are many where it's good.
So you mean you're thinking of some parameter exclusion argument, or is that what you?
Yes, I would think. You know, first you take a really. I don't know, you know, you take...
So an example where the condition is satisfied clearly, or then...
Yeah, I'm not sure that... Can you find an explicit example where it's satisfied?
Yeah. So...
there is a radius for which you know...
There are examples, the tables that I showed...
I believe...
Here, I mean, you can find explicit numbers on the... For example, on the right one or the left one, you can find explicit.
Yes. So I would say, you fix R2 and you vary R1 a little bit.
So there's just one big difference. I don't know, maybe you're thinking of the quadratic family or when
something like that.
So the big problem is that when you are the quadratic family, when you're in trouble, it's when you're close to the critical point. And so if you're close to the critical point, you're going to follow the critical orbit. But for the billiards, it's a little bit different because the trouble is happening all over the place. And so yeah, but maybe it can be done. Yeah, it's my problem. Yes, I know. Thank you.
Another, yes?
About the last part, these measures parameterized by t.
Yes.
Can you please comment on the physical meaning of this parameter? I mean, how do you realize it? For instance, if you make a numerical experiment, how can you?
Well, this I don't really know how to answer because I mean for the parameter 1, we have an obvious interpretation, right? I mean, it's about the time average for almost every initial condition. For the parameter 0, it's about counting periodic orbits, okay? And for the other parameters, I don't really know what to say. I mean, one of the things which is also part of the science fiction program, which I mentioned about zeta functions, it would be also, there's another thing which I did not mention, which we would like to know that these measures are obtained by taking the Dirac masses along periodic orbits and putting the corresponding weight and then taking the limit, right? So we want to have some equidistribution of periodic orbits. So for the measure of maximal entropy, we expect that if we take all the periodic orbits, they will be equidistributed if you don't put any weight, they would be equidistributed with respect to the MME, but we don't know this. We expect that if you take the periodic orbits and you weigh them with 1 over the unstable Jacobian, they would be equidistributed with respect to the SRB measure, but we don't know how to prove it. And now, I don't know if this answers a little bit your question. If you take all the periodic orbits and you weigh them with the Jacobian to a power which is either t or 1 minus t, depending on how you do your normalization, you accept that you would get equidistribution to the corresponding measure mu t. But despite the efforts of Jean-Pierre, I'm more a mathematician than a physicist. So maybe my chairman has a comment about it? No, so yeah. So yeah, I'm not sure this was really
related, and this T star you find is trace of some phase transition in this?
Right, so we don't claim that we get the optimal T star. It comes from a kind of trying to get a control on some spectral elements. So we don't know if it's probably not the optimal. Is there a physical interpretation? Yeah, it's a.
Can I ask you?
Yes. Yes.
There should be a T star or not?
No. We expect that. Yes, maybe that's a question which I should have understood. I didn't understand. Yes, we expect that there is a T star. We expect that there will be some number beyond which you cannot go, and it's not here in my mind enough so that I can give you the physical interpretation. But yes, we expect that there is a real T star, and we expect that the one we got is not the actual one. Yes. Yes.
So, for example, you cannot do ergodic optimization or something like that?
Probably not, no. Yeah.
Some other question in presence? It doesn't look like. No, we don't have also question in remote. Then I think we can thank Viviane again, and we adjourn for the next